Reality, captured in user-friendly symbols and processed for understanding. The Idea Channel.
So, sometimes when I run into people from outside physics, at least, and maybe closely associated sciences, and people ask me, what is it that I do? I often get a very sort of uncomprehending response. I mean, they've heard of physics, they've heard of particle physics, and they think of it as going to smaller and smaller things and figuring out what the world is made of at that level. And when I say that I work in condensed matter physics, I get some sort of puzzlement. On one notable occasion, someone thought that I was saying condensed metaphysics, which is pretty much as...
Well, every once in a while you're guilty of that.
This is true. But then I try and explain to them that there is sort of a problem in physics, which is that of starting, as it were, from laws that you know at some level and working your way back to the universe that we see around us, matter and life and issues like that. They sound often slightly surprised that something like that is in fact a problem in physics or in science generally. I don't know if you have that experience. And if you have
I have it all the time, and usually I just face it out and say I'm a condensed matter physicist and leave it at that. But I have occasionally, I even have a lecture that I've given every once in a while, saying what in hell is a condensed matter physicist. I think there are kind of two responses actually. A lot of lay people, and by lay people I mean people who are outside of physics, not.
Right.
Maybe not outside of, and maybe outside of science. A lot of lay people don't have any concept of how complete an intellectual structure of physics is. Mm-hmm. Of course, there are a lot of people who have the other view. I mean, why is it a problem? But I think it's more common that people don't recognize how much really we know, how deeply we understand the world on the level of everyday objects.
Which is interesting, since this is an understanding that's almost, one might say, roughly a century old.
Yes. Well, I was going to say that it's strictly a 20th century phenomenon. It's perhaps worthwhile to look back on it from the point of view of the end of the century. Because if you look back in the 1890s, you find that find it very hard to think yourself back to that time, when at the same time physicists were pronouncing that they really knew everything there was to know. Mm-hmm. There were people, it's supposed to be Lord Kelvin, but I don't think it actually was. There were physicists who said there's nothing for it but to look for more decimal places. Mm-hmm. And they were so wrong. They hadn't, they were in a complete blank as to the fact that there was a problem.
Right.
They hadn't seen the existence of this problem. I mean, what they saw as physics was they took matter as given. They took, for instance, a planet. They said, well, there's the planet. How is it going to move? And you use Newton's laws, and you derive that it goes around the sun in an elliptical orbit. And that's a great success. And what more is there to do? Or they studied the laws of hydrodynamics of water.
Right.
They had a perfectly good description of how water flows, invented by some 19th century physicists named Navier and Stokes, and very much elaborated by the great hydrodynamicists of the end of the century. But they had not the slightest, but very little idea of where the numbers that went into that
Right.
equation came from,
Right.
and what they represented. And then suddenly, in the 1890s, these they were brought up short by something like, well, a number of phenomena that they discovered.
Right.
The big ones were X-rays,
Right.
radioactivity, and cathode rays.
Right.
The discovery of the electron.
And the spectral lines of various.
Yeah, and they'd had spectral lines for many, many years, and they thought, well, spectral lines were another of these things. They cataloged them.
Right.
They had them measured to enormous accuracy. But they just didn't think that was their business.
Right.
And they weren't really studying that. Then suddenly they were brought up short by these new phenomena, and they realized that there was a whole level of understanding and a level of explanation that consisted of questions they'd never asked themselves. Do atoms, I mean, in the first place, they had the concept of atoms, but they'd never thought of an atom as something that they could really understand.
Right.
And they certainly had never thought we should look inside the atom and find more and more, find tinier and tinier subparticles to the atom.
Right.
And all of this became the subject of physics, rather than a set of problems that they had realized were there. The whole subject suddenly changed into a new subject, which was how do atoms work? What do atoms really do?
Right.
And that is the great triumph of the quantum theory.
Right.
With the quantum theory, we're able to really look at the properties of, well, not just ordinary matter, of course, extraordinary matter. We understand how the sun burns, how the interiors of the stars work. We understand how the interiors of the elementary particles work to a great extent.
Right.
But the really enormous achievement that took place beginning in the 1920s is that you can hardly imagine or hardly know of a piece of ordinary matter, a system consisting of the ordinary everyday objects around us that we don't have quite a deep understanding of.
Right. Sort of interesting in some ways that, as always with the great moment sort of change in physics, that it was a combination of advances in experimental technique, and as you were saying, all those, let's say, spectral lines were known, but still this conjunction of discoveries of the electron by Thomson and then the nucleus by Rutherford suddenly posed the problem in a way that was not possible to pose before you really understood what you might mean by an atom. And once you had posed the problem in terms of, let's say, a planetary solar system-like model of the atom, it became rapidly clear that the classical mechanical account of it couldn't possibly be correct.
Mm-hmm.
Such an atom would not be stable.
That's
And
right.
in fact, once you pose the problem that way, then it's clear that even the stability of matter, the fact that anything exists at all, instead of
Yeah.
collapsing onto itself, is something that requires ideas that the quantum theory was then able to provide. The notion of having particles with Fermi statistics, things that can't be in the same place at the same time, roughly speaking. So it's again, although as a sort of, since we're both theoretical physicists, it's natural for us to look at it sort of from the perspective of theory, but I think the advances in experimental technique that made it possible probably played a crucial role, as they often do in the discovery of the telescope
Yes,
and the
yes.
invention of classical mechanics.
That's remarkably true. That's the way physics works. And you can understand. No, we will be talking, I think, in the course of this conversation, we'll be talking about why it is that you so often need experiment to
Right.
to stimulate theory and theory to guide experiment. There are a couple of, there are, in fact, two aspects to this problem. In the first place, of course, we have this wonderful success story that beginning in 1925, and certainly not before 1925, we were able to understand the properties at first of atoms, and then of molecules, and then of solid matter, and now we're even beginning to deal sensibly with polymers and glass and liquids and all that. So we've had a remarkable success story. But if the story were nothing but that, then the two of us would be out of a job.
Right.
We'd just be redundant. And there's even an eminent journalist of science named John Horgan who claims that we are out of a job, that we've reached the end of science. So there are other questions that are...
That would put science journalists out of a job too.
Yeah, it would put science journalists out of a job. Fortunately. A gentleman I would be glad to see out of a job. But there are also deep problems. There are things that we haven't completely solved, even within condensed matter physics. And they keep cropping up. The notorious example, and the kind of everyone's favorite example, is the phenomenon of superconductivity. We had this marvelous experience of discovering the quantum theory, which within 5 years we had the basic explanation of why ordinary metals exist and why other substances aren't metals and insulate. But there was one class of metal that was a complete mystery and had been a mystery since it was discovered in 1911. And that was the superconductors. It was discovered by chemically honest that lead and mercury were superconductors. They conducted electricity without showing any resistance at all. And if you make a ring of lead, you can start a current flowing in that ring and it will continue to circulate.
Essentially forever.
For I calculated once the age of the universe. If you keep the lead cold. Of course, then Camerlingonis measured gold, and he claimed that was superconducting too, but he corrected himself only in 1912, so he didn't stay permanently wrong. But it wasn't until 1957 that we had even the hint of a theoretical explanation for this.
Right.
So that took 46 years after the discovery, and something like over 30 years between the discovery of the fundamental equations that explain it and the understanding of the phenomenon. But that wasn't the end of the story. In 1987, a kind of superconductor was discovered, the so-called high-TC superconductor, and awarded a Nobel Prize in remarkably short time of 1988. And those we still don't understand. Those we find are in the center of a tremendous congeries of controversies, questions, puzzlements, and so on.
Maybe if I
so
can
there are still problems.
If I can synthesize some of the things you've been saying. So one thing that you sort of didn't say, it's probably worth repeating, that modern chemistry and modern molecular biology were simply inconceivable as subjects before the discovery of the quantum theory. So when what you were saying about not being able to understand the world around us, it's completely changed the way we look at vast areas of our life and most notably ourselves.
Yes, I guess I was jumping ahead.
Right.
I think that's what you're trying to point out, and you're right. And I was jumping ahead because I didn't explain how much we knew before
Right.
I explained how much we don't know.
We don't know. But
And that was, and has been a remarkable achievement.
But what's interesting is, again, this notion that it was impossible. I mean, Schrödinger was one of the founders of the quantum theory. Unsurprisingly, was perhaps the first person to guess that once you had this understanding of atoms and molecules, that it was very natural to look for the basis of heredity, which had been indirectly guessed by the tradition of genetics and following Mendel.
Have you ever read the book?
I've had it sort of summarized. I haven't actually read it.
Actually, what is surprising about it is that he had it the other way around.
Oh, he did?
He personally felt that probably there was something in life that couldn't be explained by simple chemistry.
I see.
He was asking, what is life? And his answer was, well, so far we can't explain it. I mean, it was very influential because it asked the question.
Right.
But he gave the wrong answer.
I see. It was my understanding that he at least
Well,
suggested
he presented the two possibilities.
possibilities. I see. But
And
his
he
own
certainly did not decide between
this I didn't
them.
know. Because just recently we had a talk by an eminent biologist who spent pages quoting from Schrödinger and essentially hailed him as one of the founders of modern
Well, he
molecular
was in
biology.
that sense that he asked the question.
Asked the right
But he
questions.
didn't. Well, I'm not sure whether he didn't. Well, he certainly finessed the question. He did not
I see.
settle it finally one way or another.
Right. But coming
Uh,
back to your second thing, just to sort of try and put it together. So, as you're saying, so there's an enormous amount that we came to understand about the nature of the everyday level, the macroscopic level, starting with this understanding of atoms and molecules due to the quantum theory. But as you're
Yes,
saying,
and
the
we
example-
understand how chemistry works.
How
I mean,
chemistry
not
works.
just that there is chemistry,
Right.
but we understand in very great detail
Detail.
how chemistry works and how the fundamental empirical rules of
Yeah.
chemistry
Right.
that had been discovered before the quantum theory.
So having said all
All
of this, we
follow.
don't want to turn around and say, nevertheless, problems remain. And
Yes.
as you were saying, the example of superconductivity, that it took so long for a phenomenon to be understood. So that is due to what? After all, we know the fundamental equations, I might ask you sort of naively, and we knew them back in the 1920s. And so why is it that it took us so long to figure out how the traditional superconductors worked? What is the obstruction?
Obstruction, well, it's something that the biologists invented the word for. It's emergence.
Mm-hmm.
And another, well, the kind of phenomenon that occurs in superconductivity is something that I would classify as an emergent phenomenon, but it's a specific kind of an emergent phenomenon called broken symmetry.
Mm-hmm.
Emergence, perhaps, I don't know whether it's come up in other discussions in this series, but emergence is a terribly important concept. An emergent phenomenon is a phenomenon which occurs in a system of individual parts, simpler parts, but only when you put the different parts together is it even possible to conceive of the existence of the conceptual structure of the new phenomenon. The first example where this word was used was by the 19th century biologists, and about Darwinian evolution. They said modern life is an emergent phenomenon from primitive life, and then if you're brave enough, you say, well, primitive life is an emergent phenomenon from the laws of physics and chemistry.
Mm-hmm.
So it's...
In the case of superconductivity, you would say that a single atom of lead can in no sense be superconducting.
You can't even conceive of the
conceive.
possibility
Right.
of an atom of lead. Well, you can't conceive of the possibility of an atom of lead being metal.
Right.
And lead becomes metal only when you put all the atoms together. But in addition, it has Having take lead, put a lot of atoms together, you have either molten lead or ordinary metallic lead. And these are both metals, different kinds of metals. But then you lower the temperature still further, and you get down to about 6 or 8 degrees, I believe, in the case of lead. 8 degrees Kelvin, 8 degrees above the absolute zero. And it suddenly stops showing any resistance to the flow of electricity. But more important, it does what we call breaking symmetry. The state of the lead below this transition temperature has a new kind of asymmetry, if you like, anyhow, a different symmetry from the state of the lead above this phase transition. This symmetry is of a sort that really we hadn't conceived before superconductivity was first explained. It was something that was just inconceivable. As a matter of fact, there were mathematical theorems that had been derived that proved that theorem, that symmetry couldn't exist. It was proved right here in Princeton. Didn't you know?
No, I didn't.
And it was called not supersymmetry, superselection rules. The superselection rule says there can be no coherence between states
with different particle
number. And that is why, and as a matter of fact, Eugene Wigner opposed the theory of superconductivity for the rest of his life.
It's well before my time. I didn't realize
it was
that.
well before your time. And he was wrong. But he firmly believed in his superselection rules, which were violated by the theory of superconductivity. This phenomenon of broken symmetry, well, perhaps the example of superconductivity is too esoteric and outside of people's common experience. But there are other examples of broken symmetry which are very simple.
Right. Well, magnetism would be
one
example. So if we look at iron, there's a sense in which each individual electron has a magnetic moment, a little magnet attached to it, if you will. And at high temperatures, the electrons don't really agree among themselves on which way their little moments should point. But there comes a temperature, a Curie point, below which they suddenly decide to agree over macroscopic scales, over the size of a piece of iron. And that's when the iron goes magnetic and then it's able to stick to our refrigerators. And so this distinction that, as you're saying, that the symmetry is broken in the sense that in the high temperature phase of iron, there's essentially, if you look over some suitably average period, you find locally no signs of magnetism. But the moment you go below the temperature, you do. And the iron does that, presumably for reasons of energetics or more technically free energetics, in which it decides to give up on some of this global symmetric freedom in order to achieve more.
And there's some very important properties that the iron acquires that are consequences of the broken symmetry. It acquires a certain rigidity. I mean, the reason for the magnetism is that it acquires a certain rigidity. It costs energy to twist the magnetization in one part relative to the magnetization in another part.
Right.
So it has stiffness. It has another phenomenon. It can transmit waves. It has waves of magnetization that pass through it, called spin waves.
Right.
And these are very fundamental to the phenomenon of broken symmetry. And so this phenomenon of broken symmetry is not just the observation that there is a different symmetry, which is an important observation, but it's the observation that there are a cluster of properties which it implies.
Right.
In superconductivity, there is something like this rigidity, and it It is the rigidity of this new symmetry,
Right.
which causes the perfect conduction. It's a kind of a stiffness or an elasticity of the electric fluid, in the same sense that there's a stiffness of a steel bar, or a stiffness of magnetization of a steel bar.
Right.
But this tends to, well, perhaps we should
Well, I was
go
going
on
to say,
from there to
yeah.
this idea of the hierarchical nature of,
Right.
of
Well, I was going
knowledge.
to say it leads naturally into sort of two things that are worth
Mhm.
perhaps discussing. One is that, so we've sort of crystallized the notion that what makes condensed matter physics, let's say, a discipline, is the fact that there are these properties that emerge when we go from the microscopic to the macroscopic. And since these are qualitatively new properties, emergent properties, as you said, you're not going to learn about them by studying 3 atoms or 4 atoms. You have to study an incredibly large number of atoms and know what to look for. So that naturally sort of leads to two
That's
questions.
why we call it condensed matter physics.
That's right.
Physics,
Right.
as a matter of fact.
Right.
Because it isn't interesting to us if it isn't condensed, if it isn't a lot of atoms.
Right. So that leads to sort of two things. One is, it leads to the question of, well, if it's not something that you're able to get by simply taking a large number of atoms and, let's say, putting their equations of motion in a computer and solving for them, then how is it that condensed matter physicists ever figured out emergent properties? What is the nature of an explanation in our field? And the second sort of thing it leads to is that, which is also related, which is why are these properties comprehensible at all? And so maybe if I can start in the second one, I think an important insight that has come and perhaps was formalized in the work of Kenneth Wilson, who got the Nobel Prize for that, is this what we call in technical language the renormalization group idea, which is sort of an unfortunate name since it conveys almost nothing even to people inside the field.
Yes.
But it's the idea that physics is organized by scales. So if I look at short distances, which in some sense are also high energies, there's some physics appropriate to that level, but as I work my way up, so let's say they might be physics appropriate to the quarks inside a nucleus, as those our colleagues, the other levels are interested in studying in terms of quantum chromodynamics or theories of that kind, work your way to the sort of nuclear level and then to the atomic level. And essentially, if you've gone far enough in scale, that only some of the details that were known at one scale are truly important as input parameters into the physics of the other scale, but in the process, not everything is relevant, and properties emerge. So that physics separates by scale, which of course is responsible for two things. One, the richness of phenomena. It's not just, the universe is not a giant atom. And also in some sense makes it comprehensible, because you're able to organize physics by scale, then you can sort of leave some details aside and start. Somehow nature had been enormously complex and every scale was linked to every other scale. Perhaps we wouldn't exist to be able to ask these questions in the first place. But the thing that perhaps you might address, and I think since you've thought about these questions yourself, is how this question of explanation in condensed matter physics, how one understands a phenomenon, and in particular the importance of what people call model building.
As you were implying, the worst way to go about it is to pile one atom on top of the next one, on top of the next one, and then just compute. Very seldom can you ever arrive at any useful conclusion. One of the important insights about that process is one is always finding in the discussions of philosophers, not in the discussions of condensed matter physicists, I must say, the idea of the perfect computer. And you have a perfect computer and you have Newton's laws, or as we now know Newton's laws won't do, you have quantum mechanics. So if you have quantum mechanics, you can just compute the behavior of all these atoms and eventually arrive at the answer. There are two things wrong with that. One is you can't do it, but even in principle it's not right. Because even if you succeeded, all you would be able to do is to say, okay, this piece of lead is superconducting.
Right.
I calculate that it has all the properties that I already know exist, and their superconductivity. In some sense, you have to find an explanation that explains something to you,
Right.
that somehow simplifies it. So we have this problem of what is the nature of an explanation? And I don't think we always know exactly.
Mm-hmm.
But one of the best ways of arriving at an explanation is the process of abstraction. To take from this detailed structure, all the details of the how you have put all the atoms together, to take from this the important pieces, the atom, and abstract some kind of model which may be much easier to solve, that exhibits the phenomenon you're looking for, but doesn't show a lot of side issues. One example of this kind of abstraction is the simplest one, the one with which condensed matter physics began, which used to be called solid-state physics. Any real piece of lead or iron or whatever has to be to some extent impure. Mm-hmm. It will be full of defects of various kinds. It won't have an exactly regular crystal lattice. So a very simple abstraction is to say, well, let's imagine that it really is a perfect lattice. Mm-hmm. Then what are its properties? And that turns out to be at least in some degree, a problem that we can solve a lot more easily than we can this complicated imperfect system. Once we've solved the perfect system, we can say, what are the properties of this perfect system? And one example of a property is that it turns out that electrons can move as freely through a perfect lattice as they can move through a vacuum.
Right.
And so if we now want to know what do the impurities do to these electrons, we can make an abstraction. We can say, forget about the perfect part of the lattice. Let's just drop that out and pretend that we have electrons flowing through a vacuum, and that these electrons are scattering on the imperfections in the lattice, or they encounter imperfections of one kind or another. And that causes resistivity and various other properties. Or if we're worrying about how light is propagated in this lattice, we can ask how is light scattered by the imperfections in the lattice, without bothering too much about the properties of the background.
Right.
So we abstract. First, we make the abstraction of the perfect lattice. Then we discover that's so simple that we can just drop it out and pretend that it's really a vacuum.
Right.
And again and again and again in condensed matter physics, that was one of the earliest techniques invented. Actually as late as the 1940s by Landau. Mm-hmm. We make this equivalent vacuum, mm-hmm. and then we study how things move within that, forgetting about the absolutely regular structure, right. and asking now what are the things which are wiggly inside this regular structure.
Quasi-particle motion.
Yeah, quasi-particle approximation, or the elementary excitation approximation.
Right.
That was really invented by the great Russian physicist Landau.
Just as a footnote, actually, it strikes me that one of the great and parallel insights in modern economics also seems to have been the study of relatively simple models in which they abstract things. Of course, they have a much more sort of obstreperous system to study the actual economy that keeps changing on them. But I think much of the post-war progress in economics seems to have come from a sort of similar meta insight about how to proceed.
I could differ. I think there also has been a great tendency for an economist to be guilty of physics envy and to make oversimplified models, which then don't really.
Well, there's more at stake when they go wrong.
Yes. Well, not only is more at stake, but there is a tendency, for instance, for them to try to make models that behave like statistical mechanics, where all the actors are the same in statistical mechanics. In our physics, every atom is the same as every other atom, in some deep sense.
Right.
In economics, every actor is not the same as every other actor.
Right.
And there's a very wide distribution of sizes of actors.
Right.
And up until recently, they totally neglected this, or many of their models totally neglect this reality.
Sure, they'll fix it. But going back to what we were
They'll fix
saying
it
earlier.
with some help from physicists.
Well, perhaps. That'll keep us employed for a while to come.
Yes.
I wanted to bring up something which is related to this issue of the complexity of trying to solve for the properties of macroscopic, let's say, assemblies of atoms, which is, it is of course true that many of our colleagues who have made really an enormous amount of progress with the help of modern computers in calculating many of the properties of real materials. For example, the properties of iron at zero temperature, if you wanted to have some sense of how the size of the magnetic moment is something that they're able to do using modern computers plus some amount of analytic sophistication to
Yes,
really
and
fairly
if you had
impressive.
asked me 30 years ago, I would have been very pessimistic about their
Right.
reaching the level of
precision that they have.
sophistication that they've
Yeah.
reached now.
Right. So that's an impressive achievement that I think
Mhm.
really deserves its due, and undoubtedly as computers get more and more powerful, they will undoubtedly get better and better at it. But it's perhaps is also an interesting way it illustrates some of the limitations of looking for emergent properties by this sort of brute force approach. We mentioned the example of the magnet and the Curie point where magnetism first really sets in. And there's this sort of remarkable universality associated with the behavior near this point. In fact, that's what Mr. Wilson got his prize for. And the remarkable thing that came out of that understanding was that the self-organization of the electronic spins near this Curie point where magnetism first sets in is mathematically identical to the self-organization of molecules in a liquid and gas near what's called the liquid-gas critical point, where the difference between a liquid and a gas just about disappears. These are two completely different systems. They would require completely different microscopic technologies. And I bet no one starting with, powerful computers for
That's
the
right.
two of them would ever discover
Of
that
course.
these were in fact but
And it
by
illustrates another thing, which is the power of abstracting a model
model. Exactly
from
right.
the
The details.
from the details and saying, actually, what do I have to solve in order to get this very complicated behavior
Right.
is a model which doesn't contain either the magnets or the atoms
Right.
in any real detail.
Right.
But we also should say something about the role of experiment,
Right.
which is, well, for instance, in the case of superconductivity, I am sure that no one would ever have invented a theory of superconductivity if he hadn't had the experiment
Right.
facing him down and forcing him to find an explanation for this phenomenon. But experiment, well, in a field that you've played with or worked with, experiment has played a very important role also.
Oh, that's right. No, I think you're referring to the quantum Hall effect, for which our colleague Dan Sui got the Nobel Prize this year. And I think it's fair to say that although there were extremely mild intimations that something special might happen for a set of electrons in 2 dimensions placed in a magnetic field, that essentially, before the experimental discovery of the phenomenon, no one had a clue that anything like that was possible, this thing called the quantum Hall effect. And it's a remarkable phenomenon in many ways. The physics of it, physics is remarkable. You take a set of 2D electrons, 2-dimensional electrons, you put them in a magnetic field, which kind of is perpendicular to the plane they live in, and they have an incredibly intricate set of phases that they're able to organize themselves into sort of collective dancing patterns, as one of our colleagues, Xiaogang Wen, calls them. And it's remarkable. You change the magnetic field a little bit, and the collective pattern changes completely. You find organizations nested within organizations, hierarchical organizations in which the electrons first organize themselves, then make small defects, and then the defects organize themselves. I mean, it's an incredibly rich structure that you could never have guessed. But the field is also remarkable for several other reasons. Another purely physical reason, which I think was perhaps heavily influenced the Nobel Committee in their decision, was the fact that when you think of adding an electron to such a system, it actually doesn't go in as an electron in some sense. In an average sense, it breaks into, for example, three pieces. The example of the sort of rich behavior that you can get in a macroscopic system that, again, at the level of an electron isn't going to split into three. But at the level of 10 to the 12th electrons, it does indeed. And I think something else that's remarkable about the field is its sort of connection to technology. I mean, you were there at Bell Labs in the good old days when modern condensed matter physics was launched, study of semiconductors, which has had this sort of enormous impact on our lives through semiconductor technology, where the Hall effect is an example of a field which, in fact, the flow goes the other way. Advances in technology have made it possible to fabricate an experimental system that, you would be hard put to make otherwise.
That happened again and again, as it was a kind of a relay race, if you like. Many of, or several of Bell Labs' earlier Nobel Prizes were actually a consequence of, in a real sense, a consequence of the technology that was developed. One started with the quantum theory. From the quantum theory eventually arose the semiconductor industry.
Right.
But from the semiconductor industry arose very exciting developments in the quantum theory, not just the one that you're talking about, the quantum Hall effect, but even my own private Nobel Prize.
Right.
I was stimulated by the very beautiful measurements of a physicist named George Fayer on semiconductor samples that we were investigating because they were the semiconductors that were like silicon and germanium that we were trying to make transistors out of. So the samples he was using were available only because we had developed the technology of dealing with these samples. So even that one was technology-driven as well as science-driven.
Right.
And it's fascinating, well, like what you were talking about, the quantum Hall effect, that you can find areas in which the range of relevance goes all the way from direct hard rock technology, if you want to call it that,
Right.
transistors, computers, materials, fuzzy materials, sticky materials, and so on,
Right.
to these serious questions of how do you interpret, how do you understand how something happens, how do you understand the fractionalization of the electron in your quantum Hall samples.
The joke I sometimes like to make is that our field goes all the way from material science to immaterial science.
Immaterial science. But there is one other thing that in addition, we learn things about the tools we're using. We learn things about the quantum field theory.
Right.
And so what you learn about the quantum Hall effect can be relevant, is probably relevant, and is certainly using the same mathematics as our friends who are trying to understand the elementary particles by means of string theory.
Right.
Topology, Chern-Simons terms, and so on and so on. So essentially, by trying to build a better transistor,
Right.
You can learn how strings work.
Right.
Also, by learning how strings work,
I've
you
seen
can
the
help.
universe in a transistor.
Yeah, you
Could
can
be
see
a
the universe
modern
in a transistor.
formulation of Blake.
Well, actually, I was thinking of that Volovik, and there was this Russian physicist
Right.
named Volovik, who has recently written a paper called "Seeing the Universe in a Drop of Helium-3."
Right.
And the strange thing about it is, he's not above himself.
Right.
You really can see many of the things that happen
Right.
in the universe
Right.
happening in this droplet of one of the simplest liquids that
Right.
we know of.
Right. So this might be a good point to sort of look ahead a little bit, which is that we've talked about sort of this development really across science, but from the perspective of our own field, starting with the quantum theory, the discovery of the microscopic structure kind of working. So there's of course been those set of our colleagues who've gone the other way, who've gone
Yeah.
to smaller and smaller scales, and it's a worthwhile and fascinating enterprise where great discoveries have
Or,
been made.
or
in our own-
disappeared back into the first
Disappeared.
microsecond
Right.
of time also.
But of course it does have these unexpected connections, as you were alluding,
Mhm.
through helium-3 to the large-scale structure of space-time itself and of the universe. So in fact they're looking both at the very small and the very big. But for ourselves in our neck of the woods, you've been involved at the Santa Fe Institute in its setting up and so on. So there's a certain vision of where studies of our kind would naturally lead to, namely higher and higher levels of complexity, perhaps with the ultimate aim in some sense of understanding life itself as the ultimate complex behavior. Do you think that, how do you see the sort of tools and tricks of kinetic matter physics and its body of insights sort of dovetailing into this project?
Well, they already do in a number of ways. One may think what one likes of Per Bach, but I think he's made the case that there are aspects of these renormalization group methods, aspects of the study of phase transitions and things like that, that can be generalized to very complex systems. He studies traffic flows, he studies extinctions of species, he studies all kinds of things on the basis of what many of us feel is a considerably oversimplified model of, that comes from condensed matter physics.
Mm-hmm.
There's a big movement in evolutionary theory in biology that is studying evolution as what they call motion or optimization on a rugged landscape.
Uh-huh.
The first rugged landscape was in condensed matter physics.
Right.
It's the energy of a so-called spin glass,
Right.
as a function of the orientations of the spins.
So how does this work in evolutionary biology?
You simply postulate that the fitness landscape is a rugged landscape,
I see.
and it explains a great many of the general rules of general ideas in evolutionary biology.
Mm-hmm.
How well it explains them and whether it is any more than a metaphor is still a question of under discussion.
Right.
But at the American Physical Society in Atlanta, to which neither of us went,
Unfortunately.
there was a session on rugged landscapes in biophysics.
Mm-hmm.
And there are certain areas where it is well established that this approach, this condensed matter approach, makes a great deal of sense.
Right.
Other areas where it's still under contention. But there are ideas that we develop that certainly have application in broader fields. A good example is computer science. The question of complex optimization has had a very strong interaction with spin glass physics again. I don't know how far this can be taken, but certainly the intellectual structure is transferable. The intellectual structure of starting and or thinking of a simple substrate, thinking of emergent things that the simple objects and the substrate can do together, making a new level of the hierarchy. For instance, we start with physics of atoms. The atoms make molecules. That's simple. But then the molecules can get together and make the secret of life, the heredity, and proteins, and the complex set of catalysts that life is based upon, and the complex network of proteins turning on genes, turning on proteins, turning on genes, this complex network that life is based upon. Then life develops nervous systems, or it develops morphology, and we begin to understand that. But then when we get to the nervous system, which is perhaps the next stage beyond morphology, that's where the frontier is at the moment. And of course, once you have organisms that can think, more or less, once you have intelligent life on Earth, if we have intelligent life on Earth, then we have sociology, and then we have the organization of more and more complex states, and so on. So you can see the hierarchy working all through the different areas of science. And you also see this unifying thread, which Edward Wilson has called consilience, which is the requirement that at each stage in the hierarchy you have to look downward and see whether what you think about the stage where you're at is consistent with the laws that you know are true at the lower stage, and so on.
I think he makes the point in that book, which I think is clear to most practicing scientists, but it's probably worth, even for us, for him to say it in the detail in which he has, that we really are at the risk again of some hyperbole, at a stage where I think we're about to start understanding ourselves at a level of detail that's really going to be quite staggering. The sort of marriage of microbiology and perhaps ideas from computer science and, as you said, from spin glass theory and physics about complex systems and their...
Of course, I'm always a pessimist about these things. I'm usually wrong. I was wrong, for instance, about morphology, about the remarkable progress that's been made in the past 10 years, learning how bodies are organized. I thought that was one of the insoluble problems that was going to have to wait for the 21st century.
I think there's just two rules in this regard. One, it often takes longer than you think, and second, it often happens sooner than you think.
Yes, of course.
And perhaps we'll come back fairly soon. And
well, the trouble with the future is, of course, that the trouble with prediction is that it's very easy so long as you aren't trying to predict the future.
So maybe on that note, we'll
Okay.
call it quits for today.